Hi everyone, my name is Turcanu and I'm a postdoctoral researcher at the University of Luxembourg. Today I'm going to talk about our work on decentralized congestion control in vehicular networks from an age of information perspective. This work has been carried out in collaboration with Professor Andrea Baiocchi, Dr. Nikita Lyamin, and Professor Alexey Vinel. Okay, so let me start with why we think congestion control is important in vehicular networks in the first place. Well, the main communication paradigm in vehicular networks is based on a continuous update message exchange. Namely, vehicles are exchanging periodic messages containing basic status information that is needed by vehicular safety applications. Well, since the wireless communication channel used by vehicles to exchange this information is highly unreliable and the spectrum is limited, controlling the congestion is crucial. In this context, both information reliability and freshness are very important. Unfortunately, existing solutions typically optimize either the channel load or the information freshness. And as a consequence, the performance evaluation is also performed focusing on one of these two aspects. Well, in this work, we try to fill this gap by providing a comprehensive performance evaluation of the existing DCC solutions, looking at this from the point of view of both channel load and information freshness. We also provide a performance bound based on centralized collision-free scheduling. Okay, so let's describe the adaptive rate control algorithms, and let's start with the ETSI, with the one standardized by the European Telecommunication Standard Institute, known as ETSI DCC. Now, ETSI defines three main techniques to control the congestion: transmit power control, transmit rate control, and transmit data rate control. In this work, we are going to focus on the most common one, which is the transmit rate control. And here, ETSI defines two main approaches: reactive and adaptive. Both these approaches use the current channel load as an input parameter and adapt the broadcast interval accordingly. Right? So the performance metric that measures the channel load is known as channel busy ratio. So every vehicle defines the channel busy ratio as the fraction of time the channel is sensed busy by this vehicle over a total observation period. So these algorithms, they take the currently measured estimated CBR in input and then adapt the broadcast interval accordingly. Very briefly about these two approaches. So the reactive approach is based on a finite state machine composed of three main states: relaxed, active, and restrictive, where the active state can be further divided in multiple substates. In this work, we focus on a finite state machine with three active states. Every state is characterized by a certain packet transmission rate or broadcast rate. For instance, if a vehicle is in the relaxed state, it can transmit at 10 Hertz frequency, or it can transmit 10 messages per second, while if a vehicle is in the restrictive state, it can transmit at most one message per second. And the transition between the different states is also based on the measured CBR values, as you can see in this figure. Now, the adaptive approach is slightly different. In here, every vehicle computes the moving average of the locally estimated CBR value, and then tries to bring this computed average of a CBR value to a certain CBR target level. Okay, so I'm not going to describe everything in detail because these are well-known approaches and they are also described in the paper. Now, the second approach is known as AOI-based adaptive approach. AOI stands here for age of information. And as you can already guess, this approach, unlike the ETSI DCC approaches that take an input this channel busy ratio, this approach takes the locally estimated age of information as the input parameter and then adapts the broadcast interval in order to minimize the AOI, the system AOI. Okay. Now, Age of information is a relatively recent metric that has been introduced to measure the information freshness in systems where nodes exchange periodic messages. And the vehicular network is a perfect example of this kind of system. So again, I'm not going to describe in detail now how this algorithm works, but you can find the details in the paper. The important thing to remember is that it uses the AOI, the locally estimated AOI in input to adapt the broadcast interval. Now, both ETSI DCC approaches and the AOI adaptive approach, they are decentralized mechanisms, meaning that vehicles base their decision or they adapt their broadcast interval based on locally estimated information. And clearly this is not ideal because vehicles can send messages at the same time, so there could be simultaneous transmissions, which could lead to packet collisions, to information loss, which ultimately has a negative impact on both channel load and information freshness. So to actually better assess the performance of these decentralized mechanisms, we decided to come up with a centralized approach that creates a collision-free scheduling, right? So where there is no information loss, in order to better understand how far are these decentralized approaches from the ideal case. So sort of provide a benchmark. And this, we call this approach central schedule. And it is essentially a heuristic based on sequential two-hop graph coloring that assumes global knowledge of the network connectivity graph. Now, the connectivity graph, in this graph, the vertices are represented by vehicles, and the edges, so there is an edge between two vehicles if these two vehicles are in each other's communication range. And the goal of central schedule is to find a minimal length conflict-free broadcast schedule. What does conflict-free means? Well, in our case, a conflict-free situation is when two vehicles are more than 2 hops away. So let's see an example to better understand. Actually, the central schedule is composed of 2 main steps. So in the first step, the algorithm will find the minimum number of slots that are needed to schedule all the nodes in the graph to transmit exactly once. Okay, so let's look at this example on top. We will visit the graph in the following order. So let's try to assign, central schedule tries to assign node 1 to find a slot, right? So node 1 will be assigned to the first, to transmit in the first slot. Then when it tries to assign node 5, well, node 5 cannot be assigned in the same slot as node 1 because they are in the same they are in each other's communication range, and there will be a conflict or a collision if they transmit in the same slot. So clearly node 5 will transmit in the next slot, in slot 2. Same for node 2. Node 2 cannot transmit in the same slot as node 5, but neither in the same slot as node 1, because if 2 and 1 transmit at the same time, there will be a collision at node 5. Okay, so same holds for node 7, who will be scheduled in the slot number 4. But what happens to node 8? Well, node 8 cannot transmit in slot 1 because it will create a conflict situation with node 1. But node 8 can transmit in the same slot as node 5 because they are more than 2 hop away separated, right? So 5 and 8 can transmit at in the same slot, which is exactly what the algorithm does. And then this process is repeated for every node in the graph. So essentially, the output of this first step is a schedule table, as seen here, where every node is scheduled to transmit exactly once, and this provides the minimum number of slots necessary to do this. All right. So this table is given an input to the second step then of the algorithm that tries to maximize the number of nodes that are being scheduled in the same slot. Just to give you an example, if we look at node 5 currently, only node 4 can transmit. But if we look at the connectivity graph, node 1 is 2 hops away from node 4. So meaning that node 1 could also transmit in the same slot as 4, which is exactly what the second step does. So it will assign node 1 to transmit both in slot 1 and in slot 5. All right, so let's have a look at the performance to evaluate actually the performance of this algorithm. So we use a realistic simulation framework composed of Sumo, Omnet++, and Veins, which is a realistic vehicular network simulation framework. We also use a realistic mobility scenario that characterizes the mobility traffic the traffic patterns in the city of Luxembourg over a 24-hour span. And here we simulate an area in the city center, a 2.5 by 2.5 kilometer area. To avoid border effects, we only collect statistics in a smaller region inside the simulated area, which is a 1.5 by 1.5 kilometer area delimited by this dashed line here. In this table, you can find the main simulation parameters. You can find more parameters in the paper itself, but the main thing to remember here is that the decentralized approaches, they are implemented as applications running in each vehicle's onboard unit, while the central schedule is implemented as an Oracle application, meaning that only the V2V links are explicitly simulated in order to obtain the current connectivity graph, but the V2I links are assumed ideal. Okay, so let's have a look at the results. The first thing that we want to look at is the system age of information when we vary the beacon length on the x-axis, right? And the first thing that we can notice is that central schedule indicates which is the lowest achievable AOI. So this is the black line here. Right, so the central schedule gives the best performance in terms of AOI, and this is actually the best that the other approaches can do. And now we can have an estimate of how well the decentralized approaches are doing. And among them, we can see that AOI adaptive is the one that performs the best, essentially mainly because AOI adaptive has been designed to minimize the age of information, right? The ETSI DCC approaches, they are performing worse than AOI adaptive, with the DCC adaptive being a little bit better than the DCC reactive. Now, if we look at the channel busy ratio, we find a couple of interesting things here. So first of all, the central schedule keeps the CBR constant, as you can see here. And this is exactly what we would like ideally from a DCC algorithm, right? Keeping the CBR constant independently of the beacon length size, while minimizing the age of information. Now, the ETSI DCC adaptive approach is the one that is closest to this kind of a behavior, because DCC adaptive tries to reach the CBR target faster than DCC reactive, whereas DCC reactive is a bit more sensitive to the CBR variations. The algorithm that performs the worst in terms of CBR is AOI adaptive, because AOI adaptive is less sensitive to the channel load variations, because again, by design, it tries to optimize a different metric, the age of information, not the CBR. All right, so to conclude, what are the main takeaways? First, we provided a detailed performance evaluation of the main state-of-the-art congestion control mechanisms for vehicular networks. We described a heuristic that provides performance bounds to each of the considered metrics. And then the simulation results show that focusing only on keeping low the channel load can lead to higher AOI values, which means that safety critical information can become obsolete. On the other hand, if we focus on minimizing the information freshness only, then this can lead to higher CBR values, which has a negative impact on the information reliability. For this reason, as a future work, we would like to design new congestion control mechanisms that consider both CBR and AOI variations. This concludes my presentation. Thank you very much.